What is darkness? Seriously, think about it. What is darkness? Most people think of darkness as something, like a substance, like it's made of dark stuff. That's wrong. That's really wrong. Darkness is not made of anything. Darkness is not a substance. Darkness is not energy. Darkness is not a force. Darkness is simply the absence of light. That's all it is. It's the absence of photons. Nothing more, nothing less. You see, light is made of particles called photons. These are real things. They have energy, they have momentum, they travel through space at a constant speed of about 300,000 kilometers per second in vacuum. But darkness is just what you get when there are no photons around. It's like asking what coldness is made of. Coldness is not made of anything. It's the absence of heat. Dryness is not a substance. It's the absence of water. In the same way, darkness is the absence of light. Now here's where it gets interesting. If you want darkness to appear somewhere, all that has to happen is that the light has to go away. And here's the crucial thing. Light travels at 300,000 kilometers per second to get away. But darkness doesn't have to travel anywhere. It appears instantly wherever light leaves. Think of it this way. Imagine you have a room that's completely dark. Now you turn on a light bulb. What happens? Light spreads out from that bulb, moving at 300,000 kilometers per second in all directions. It takes time for that light to reach the walls of the room. But when light was present before you turned on the bulb, and then you turn on the bulb, well, the light doesn't need to travel to be there. It just appears. The darkness doesn't need to go anywhere. It just stops being there. Let me give you another way to think about this, and this is very important. Imagine the sun is shining on the earth right now. The light from the sun takes about 8 minutes to reach us. Now, what if the sun suddenly turned off? What if it just disappeared? Boom, gone. When would we see the effect? When would the earth become dark? Well, the light that's already on its way to us would arrive for about 8 minutes. But after those 8 minutes pass and no new light arrives, boom, darkness. But here's the thing. The darkness doesn't travel from the sun to the earth at the speed of light. The darkness appears instantaneously where the light was. The darkness is essentially saying, where light is not present anymore, I appear. There's no speed involved in that because darkness isn't going anywhere. It's not moving, it's not traveling, it's just an absence. You see, this is why darkness is, in a very real sense, faster than light. Light has to go somewhere. Light has to travel. Light has to move from one place to another at a specific speed. But darkness doesn't have to do any of those things. When light stops being somewhere, darkness is already there, instantaneously. Now you might say, wait, Feynman, that's playing with words. That's not really physics. And you know what? You're partially right. But let me explain what's really happening at a deeper level, because there's something genuinely interesting going on here in quantum mechanics. In quantum mechanics, when we talk about light, we're talking about photons traveling from one place to another. But here's something weird that I want to tell you about. When physicists do the detailed calculations using quantum mechanics, and I mean the really detailed ones, they have to consider that a photon can actually take all possible paths from point A to point B. All of them. Some of these paths are straight, some are curved, some of them, get this, some of them require the photon to travel faster than light. Now this sounds like it violates Einstein's theory, but it doesn't. Here's why. These paths where light travels faster than light don't contribute to the final answer in a way that lets you use them to send information or to communicate faster than light. They cancel out. The amplitudes for these faster than light paths interfere with each other in such a way that the net effect is only the paths that go at or slower than the speed of light matter in the end. But they're there. In the calculation, these weird faster than light paths have to be included. But there's something even more interesting that was discovered fairly recently. Scientists started thinking about something called dark states and bright states of light. Now listen carefully, because this is beautiful. When light interferes with itself, remember the double slit experiment where you get bright and dark bands? Those dark regions are not just places where light is completely absent. No. In quantum mechanics, even in those dark regions, there are photons present, but they're in what's called a dark state. They can't excite a detector. They can't make an atom jump up to a higher energy level. They're invisible to normal measurement, but they're there. What this means is that even in the darkness, in those regions where we see complete darkness in an experiment, there's actually light present, but it's in a quantum state that makes it invisible to us. The light and darkness are not opposites in the way we think about them. There's actually structure in what we call darkness. There's hidden light that we can't see, with our normal ways of measuring things. This is getting at something profound about the nature of light and darkness. The physicist Gerhard Rempe and his collaborators at Max Planck Institute showed that classical interference patterns, the bright and dark bands, come from entangled states of light. Bright states that couple to detectors and dark states that don't. Both of them are made of photons. Both of them are light. But one type is observable and the other type is not. So when you think about it this way, darkness isn't really the absence of light at all. Darkness is light in a state where it can't interact with us. It's light that's hidden from our observation. It's light that's there, but in a form we can't detect. Now let me tell you another interesting thing about this, because there's more to it. In quantum mechanics, the vacuum, what we think of as completely empty space, is not empty at all. It's full of photons. These are virtual photons. They fluctuate in and out of existence constantly. In a trillionth of a second, they pop into existence and then pop back out. There's energy in that vacuum. There's light in that vacuum. But it's hidden from us. We can't see it directly. We can only detect its effects. You might call that darkness, but it's not really darkness. It's invisible light. It's light in a state where it doesn't interact with normal matter in the usual way. Some of the most profound physics of the last century has come from understanding that this empty space is actually full of things. So let me bring this back to the original question. Why is darkness faster than light? The answer is actually quite simple when you understand what darkness really is. Darkness is not a thing that travels. Darkness is the absence of light. Or more precisely, darkness is the state where light is hidden from observation or not present. Since darkness doesn't have to travel anywhere, since it doesn't have to propagate at any speed, it can be thought of as instantaneous. It's everywhere light isn't in an instant. Meanwhile, light has to go somewhere. Light has to travel at a specific speed. Light takes time to get from here to there. In that sense, darkness is faster. But it's a strange kind of faster, because darkness isn't really going anywhere. It's not like a race where darkness wins. It's more like darkness doesn't even enter the race at all, while light has to run. Here's another way to think about it that might help your intuition. Imagine I'm in a completely dark room. Now I switch on a light bulb in the corner. The light spreads out at 300,000 kilometers per second. But here's what's interesting. In the parts of the room where the light hasn't reached yet, is there darkness? Well, yes and no. There's an absence of light from the bulb, but there might be other light sources. There might be light coming in through cracks. There might be quantum fluctuations. But classically, in the parts of the room the light hasn't reached, we would say it's dark. Now here's the thing. The light doesn't have to come from my bulb to fill those regions. Before I turned on the bulb, if light was coming in from outside or from other sources, those dark regions weren't really dark. The moment I turn on my bulb, light starts traveling outward. But the regions where the light hadn't reached yet, they don't become less dark gradually. They become illuminated when the light gets there. Before that, they were in darkness because there was no light there, from my bulb at least. But if the light that was coming from outside suddenly stopped coming, those regions would become dark before my bulb's light could reach them. The darkness wouldn't wait for light to travel. It would appear instantly when the external light stopped. You see what's happening? The darkness doesn't have to be anywhere. It's always ready, it's always waiting. Wherever light stops, darkness is immediately there. Light, on the other hand, has to actually go somewhere. Light has to move. Light has to propagate. And that takes time. Now, there's something philosophical here, too, that I think is worth pondering. We often think about light as the thing that reveals the world to us. Light lets us see. Light creates reality in some sense, at least the reality we can perceive. Darkness is what we call the absence of that. But when you look at this carefully, when you study quantum mechanics carefully, you realize that this isn't quite right. Light and darkness are more intertwined than that. They're partners in the dance of the universe. In quantum mechanics, particles don't have definite positions until we measure them. They exist in a superposition of states. They exist in all possible states at once, in a sense. And when we measure them, when we shine light on them, the superposition collapses and we see one state. Before measurement, in the darkness of ignorance, all possibilities exist. After measurement, in the light of knowledge, one reality emerges. It's poetic, but it's also true. The darkness isn't the opposite of light. The darkness is where all possibilities live. The light is what picks out one of those possibilities and makes it real. So when someone asks you, why is darkness faster than light? You now know what they're really asking. They're asking about the nature of light and the nature of darkness. They're asking whether darkness is a thing that travels, and the answer is no. Darkness doesn't travel. Darkness is the absence of light, or the absence of observable light. Darkness is what's there when light isn't. And since darkness doesn't have to go anywhere, doesn't have to propagate at any speed, you could say it appears infinitely fast, or instantly, wherever light leaves. Light, meanwhile, is constrained by the laws of physics. Light can't go faster than itself. Light is the cosmic speed limit. Light has to follow the rules of relativity. Light is bound by the structure of space-time. But darkness is free from all that. Darkness just is. Now here's something I want to leave you with, because this is the real punchline of this whole discussion. In the universe, darkness is actually more common than light. Most of the universe is dark. Most of the matter in the universe is dark matter. We can't see it. We can't interact with it easily. Most of the energy in the universe is dark energy. We don't even know what it is, but it's there, pushing the universe apart. Even in regions where we do have light, most of it is hidden from us in dark quantum states that we can't observe directly. Light is the rare thing. Light is the special thing. Light is what breaks the darkness and reveals the structure of the universe to us. But light is also limited. Light can only travel at one speed. Light has to follow the rules. Light has constraints. Darkness, on the other hand, seems unlimited. Darkness is everywhere when light isn't looking. Darkness responds instantly to the absence of light. Darkness is the default state of the universe. The universe started in darkness. Before stars, before light sources, it was all dark. Light is what appeared later. Light is what's temporary in the cosmic sense. Light is what's precious. So why is darkness faster than light? Because darkness doesn't have to go anywhere. Because darkness doesn't have to obey the cosmic speed limit. Because darkness is not a thing that travels. It's the absence of a thing that travels. And that absence can be instantaneous. That absence can fill the universe in a blink. Light takes its time. Light follows the laws. But darkness is already here. That's the Feynman verdict on darkness and light. And if you think about it, it's not really about speed at all. It's about the fundamental nature of reality. It's about understanding that not everything we perceive is what it seems. It's about realizing that absence can be just as important as presence. It's about seeing that the universe is far stranger and more interesting than our first intuitions tell us. And that, my friends, is why physics is so much fun.